So I'm Noor Sajid. I'm based at the Wellcome Centre for Human Neuroimaging at University College London. So I'm a graduating PhD student, which means I've submitted my thesis, but I'm hoping to defend soon. So we'll see how that goes. And I've been doing my PhD with Friston in theoretical neuroscience. So today what I'll do is I'll present some of our work that's looked at scaling up active inference and trying to understand the types of computations and changes that you need to make in order to scale up the standard active inference regime that I'm sure most people here are familiar with. Okay. So before I get started, what I thought would be nice is to just have a quick primer for those of you who might not be familiar with the framework and the sort of notation that I'll be using throughout the tutorial. One thing that I wanted to highlight is that active inference is a tool that you can use. It's a biologically plausible decision-making framework that allows us to design and think about the ways cognitive systems might interact with the environment. And it's also a nice way of instantiating artificial agents under a model-based framework. So at a high level, what it does is that it proposes that agents that we are instantiating hold some sort of internal model that's constantly making predictions about the environment, and the predictions are updated based on the sensory data that's sampling at any given point in time. So in the literature, which is quite nice, it's been used to explain a diverse set of cognitive processes, including learning, perception, inference, etc., but also used to simulate psychological disorders and neurological disorders as well. So if anyone in the audience who's interested in the neurological side, please feel free to reach out after. So that's my area of research. Okay. So let's formalize this a little bit. So in active inference, what we're interested in, so let me just, okay. Can you see that? Okay, perfect. So what we're doing is in active inference to instantiate the internal model that I just talked about. We introduce 3 sequences of random variables across time. The first one is observations. The second one is latent states, S, and then we've got actions as well. So this allows us to define the gender model, which we have as the joint distribution, and we can factorize that out into some priors that you see in the purple here, the likelihood, which is in blue, and the transition function. So once you define the simplistic gender model without thinking about model parameters, etc., you can fit this model to observations using surprise or minimization or the variational free energy. So this is pretty standard, and the formulation essentially ends up being a KL divergence between the variational distribution that we have in blue here and the joint probability distribution that we just saw. By optimizing this bound and surpriser, we're able to actually calibrate the data that we have to the model that we've tried to fit. For action selection, we then take this model and use it to do some sort of planning or trying to select or decide what to do next. So for that, we are hoping to minimize the expected free energy in the future. And we derive the expected free energy the way it's generally done in the literature is by supplementing this additional expectation under the approximate posterior with the likelihood that we have here. And this gives us this predictive posterior that we're interested in. So at each time point, what you do is with this expected free energy, you sum it over time, and then you do a softmax over it to give you the posterior over actions, and you sample that in order to select the next actions. So this way of formalizing action planning gives us a formal way of actually scoring each possible trajectory or action in terms of its ability to reach a preferred latent state or outcome of interest. So here what that means is that we're essentially defining some sort of preferred future observation. So we don't have an actual reward function, but we have something that's very analogous, but can be written out as a multi-objective way of trying to define what the agent would like to do in the future. So selecting actions in this way has some nice properties. It naturally accounts for intrinsic and extrinsic imperatives. And the first expectation is the information-based exploration that we're interested in that leads to curious sort of information-seeking behavior. Okay. So that was a sort of a quick spiel of the standard active inference scheme that we've been sort of familiar with in the literature. have really nice properties when agents are operating in stochastic environments. So one thing we did at the start of my PhD was look at discrete active inference framework and try and see how, when you go from a deterministic setting to a stochastic setting, whether how the behavior might change. So we evaluated this in a modified frozen lake environment. So I guess the details aren't that important here, but the idea is that the rewarding location is alternating between different time steps, giving some sort of volatility or stochasticity in the environment setup. So you can see in terms of the performance how that is shifting. So we compared it with a standard, a really simplistic Q-learning agent and a Bayesian model-based RL agent using Thomson sampling. For the Q-learning agent, we evaluate different epsilon greedies, which we're seeing in the first two rows. And then the Bayesian RL agent that we're seeing in the third row of these graphics, and then the active inference agent that we're seeing on the bottom. So in the deterministic case, what we can see is that all agents, irregardless of sort of the algorithmic formulation in this simplistic setting, are able to perform really well. In the stochastic setting, where the rewarding location is changing after every n step. So here denoted by this gray line, we can see this really nice performance convergence in the active inference agent, where we have this one-shot learning happening after every n steps where the rewarding location changes. This doesn't happen with the other two, two algorithms because they have to sort of unlearn and then relearn what has shifted in the environment. So that was quite nice to see. And it sort of spoke to the potential in terms of modeling meaningful behavior using these type of schemes. But most of the work, at least when we started our own work, was restricted to low dimensional discrete state space settings. So in this tutorial, what I'm going to try and sort of convince you is that we can go beyond it and start formulating deep active inference agents for visual control. And that's something that's been predominant in the literature sort of coming out from Ghent, but also the Sussex group and lots of other folks. So it's probably not state of the art. I think that's the preface, but it's one way of instantiating the agent when you're thinking about scaling up some of the computations. So what I want to do, just to kick off the tutorial, is to get everyone to either join the QR code that we have here or the link. So make sure that you're signed into your Google account. And then once you have the link open, just click File and save a copy in the drive to create your own copy. And then we'll start. So I'll give us a couple of minutes to sort of set up. So once you open it, it should look something like this. Oh, sorry, I'll just go back again. And if you don't have a laptop, maybe pair it with someone who's sitting next to you who does have one, so you can see what's happening. Also, while people are setting up, are there any questions or comments that anyone has? Okay, once you're on it, I would really appreciate, sorry, I'm just gonna, the joys of having two screens, but if you could run up till this point where you're loading your custom libraries, that would be great. So I just want you to install all the libraries that we need, get the the source Git repository, download the data that we're going to be using, and just make sure that everything's downloaded. So it should look something like this, and then also have the custom libraries imported. Yeah. Sorry, could you speak up? You can't install the libraries, or? It shouldn't fail on downloading the libraries because it's just a standard Colab setup. Is it failing for you? Or so I guess I should preface that, make sure that when you're allocating your Colab that you have a GPU access for the session. But if not, that's fine as well. It'll just not do anything useful. Yes. Yes. Sorry. It's oh. Yeah. So I think the QR code might be the easiest option. Um, Um, are there some people in the crowd who've managed to successfully install the libraries? Okay, I see a few hands. That's good. What about the rest? Are you struggling to access it, or is it the installation of the packages that's problematic? Um, um, so you can't that's not working. So have you changed your directory? So I think one thing, so it's not going to show up for me at the moment because I don't have it. Okay, let me just. So the reason it might not be picking up is either you haven't downloaded the Git repository. So if that's not been downloaded, then you haven't been able to change the directory, which means there's no source file. And you should also give access when the Google Drive asks you. So if it's not accessing it, it can't do anything. So you can't actually run any of the code. Okay. So I think because is there a way to so because I'm sharing, my pop-ups aren't coming up, so I can't actually allow myself access to the stuff, but I think it should be fine. Okay. So I'm going to move on to the next bit, otherwise we'll run out of time, but I'm hoping that majority of folks have been able to download all the packages and okay, perfect. Sorry. I think it's like because it's on the pointer, it's hard to. Okay, so you should have also done that. If you haven't, then something probably did go wrong after that. Okay. So I'm going to move on to the next bit. Just if you haven't been able to get the Colab notebook up and running, please sort of share with someone who has been able to, so you can see what's going on. Just because it will be really hard to follow the code otherwise. Okay, so the first bit that I wanted to do was start off with how we would even define a deep active inference agent's generator model. So this part of the tutorial is just going to focus on that. But before I continue, I just wanted to highlight that this work in the code was done in collaboration with Zephyrus Fontes, Pedro Mediano, and Carl Friston. So I guess, yeah, so let's move on to the next bit. So the generator model that we're looking at is exactly the same as before. So we've got our likelihood function, we've got the transition, and then we've got our approximate distributions. The only thing that we're shifting here in this particular specification of the generator model is introducing this amortized habitual network, or the approximate over our actions. So this will become a little bit important later down the line when we think about actions. But for now, just bear in mind that this is sort of a deviation that we have from the previous specification that we saw. So in order to define this generator model, what we end up doing is essentially parameterizing each of the model parameter or the probability distributions using some neural networks. So the joint distribution that we saw previously, so the transition and the likelihood are parameterized by the theta parameters, which denote the weights of the neural network. And then the approximate distributions that we have are denoted by phi. And what's nice is that in order to land this formulation, we can just use amortized variational methods to instantiate the same partially observable MDP that we have. So there's nothing changing here apart from just the fact that we're instantiating each of the probability distributions as neural networks. But the key shift that we do is that in order to optimize it, instead of optimizing a set of free parameters for observation, which is what you would do if you were thinking about a discretized active inference formulation, if you were using the SPM code, we're now learning parameterized maps from the observation space. So this observation space to the parameter space, which is both the state space or the latent states that we're compressing, and also the actions. Okay. So I'm going to switch over to the Colab notebook just to show what that looks like. This is quite hard. So before I do that, I just wanted to ask him, is it possible to share this, like duplicate this one without, because otherwise I keep having to look back and it's super hard to. Okay, perfect. Now I can see it. Okay, great. So I think the first thing I wanted to highlight is that if you downloaded it properly, you should be able to have this folder. And this is where you have your source files. So this is where we call the custom libraries. So you should be able to essentially load that. And this should be the format. So you can see that in your My Drive or whatever, however you have specified it, and make sure that it's set to the current directory. Otherwise, it won't be able to load. Okay. So first we define our the lower part of the model, which is the likelihood and the variational distribution over the latent states. And it's super simple in terms of the specification. So we're using a convolution variational autoencoder. And the key thing to highlight here is that we've got our encoder, which is taking our image that we have. So we're specifying it in the input layer. So you've got the resolution that you're defining and the number of color channels. And then you're just doing a forward pass using 2D convolutions and then some fully connected dense layers. And then the actual latent representation that we have here is a concatenation of your latent states times 2, so whatever dimension. So here we're just using 10, so a really low fidelity model. And you can scale it up and make the architecture a lot more complex. But I guess for ease of understanding, this is what we used in the work that I was talking about, but also just making it easy to follow what's going on. And then the P of O, which is the likelihood, and allows us to actually have the emission model. We're taking the dense layers that we have, and then we're just doing the transpose of the convolution layers to get the full image back. So you can see the output. So the key difference, which will become really relevant for us, is the fact that when we're doing the forward pass, we can do different ways of doing it. So one is just using the reparameterization trick, where you're just sampling from a Gaussian noise and then just multiplying that to your variance and adding the mean to get your sample or the latent sample. But you could also just do it as a deterministic or assume a direct delta function, where instead of doing the reparameterization trick, you're taking the latent states that we had and we concatenated it to, you're just splitting it up. So in terms of the computations for the expected free energy, this becomes a little bit useful for us, but I just wanted to highlight that's the main deviation from a standard autoencoder that you would have. Yes. So the standard variational autoencoder would use the encoder as a sample. We're using the reparameterization trick to get the sample from your posterior. So you're just reparameterizing this, right? And the reparameterization trick is just taking the exponential of the log variance that you calculate. So this would be the encoder output that you get. So this encoder output. And then you multiply it with some noise and you add in your mean to get the sample or the sufficient statistic. And then the encoder bit is you're just splitting it into two. So you're not using the reparameterization trick. So you're assuming some sort of direct delta function over it. So it's like a mean. Does that help? Yes, so for that, we would do that. So this would be the encoder with a sample. So that would be the standard variational autoencoder. The encoder, so there's two functions. So the encoder with a sample is the standard formulation, and the encoder is where we're assuming some sort of direct delta function over the density, and then not actually using the reparameterization trick to sample. Okay. Any other questions? Okay. And then we're using the transition network. So this is also pretty straightforward. So I guess most state-of-the-art work right now would be using like an RNN, and you could easily replace it. But we've just got a simple feed-forward network here. And it's, again, really low fidelity. So the input is, yes. Sorry. Oh, I thought that was a question. Okay, it's getting a little bit hot, which is good. So the input layer for this transition network would be your latent state plus the action dimension, because if you remember, like when you're transitioning, you're conditioning on the next, you're conditioning the next state based on the previous state and the action. So we're just concatenating that information and passing it through our feed-forward network. And the output is, again, the concatenation of the two latent states. And this allows us to get the transition with the sample or just as a direct delta function that I talked about before. The last bit that we have is the habitual network, which is this approximate over actions. And here we're taking our latent state encoding and popping out some prior over the policy or the action space. And the big difference here is that instead of using continuous distributions like we did in the transition network, and also the likelihood and the variational encoding, we are using a categorical distribution. Okay. Are there any questions so far or comments? So if you have the Colab notebook, even if you haven't managed to like get everything running, you can still follow the code. So this gives you an idea of like how the setup was. I guess the key thing I wanted to highlight here is that the architecture is really simple, but it would depend on the type of problems that you're considering. So when we look at the data that we considered, you'll understand why we don't really need to have a fully fleshed out transition dynamics or a more complex encoding architecture. Okay, so I'm going to. It's this latent state that we have. Sorry, say that again. So the state is parameterized as a multivariate Gaussian with independent covariance. So we're just encoding the sufficient statistics of that. But we're learning the encoding over time. So so in like a standard discretized formulation or something where like you are manually writing it out, you would say, or you would specify exactly what that would look like. Here we are trying to learn it based on our optimization scheme. Yep. Oh, so we'll get to that in a moment in terms of what they actually represent and how they correlate to the data set. Yeah, but it's entirely dependent on the formulation. I think with deep architectures, what you're thinking about is the parameterization that you want over your structure, and then the data defines what's actually learned depending on the optimization objective you define. Mm-hmm. We don't have targets for the latent state. So there's two ways of defining it, and we'll get to it in a moment. One is you have a policy independent way of learning the latent representation, where you would have an uninformed prior, and then you're just essentially optimizing the KL divergence between that and your posterior estimation. Or you could have a policy conditioned, where you are conditioning on the action, so your prior is actually moving depending on what was the previous encoding that you had. So we do both, and that's because of like reasons where if you haven't really learned your model, then you want something that's very uninformed, so you don't end up in a suboptimal regime. And then over time, you shift over into a more informed prior, which is a policy conditioned. Okay. Okay. So let's see if this works. I'm going to. Nope. Okay. That's all right. So I guess the helpful thing is that because everything is quite standard so far, we're going to just make use of the standard variational inference machinery to calibrate the model to best reflect the data. So we just use stochastic gradient descent to update this using the surprise or minimization objective that we saw right at the start of the presentation. So what does that look in practice? So I'm just going to end this show again because otherwise I can't see. Okay, cool. So we're going to define the generative model losses. And this goes back to the question that we just had in terms of what does the optimization objective look like. So you'll notice that I've labeled them different terms. So this is just optimizing your cross entropy practically. And then your term B and C are essentially going between an uninformed prior and a policy conditioned prior. So if we look at computing the loss, essentially the terms are written out explicitly with A, C, and B. And then we've got a gamma function that we are using to go from using the uninformed prior to an informed prior. Then you have the transition function, which is essentially the same as the KL divergence that we have here, but it's just for the next time step. So one is encoding the loss function for the current time step, and the transition function is doing it for the next one. So this can be a little bit involved. So what I want to do is just take a few minutes now for people to have a look through. And I guess also if anyone's interested to see how we're actually optimizing this model using the loss functions I just defined. So I wanted to just show quickly, so the TF loss file that you can just open up. So I'm hoping everyone can do that on their own Colab notebooks, but essentially the key difference to, I guess, more recent stuff where it's an end-to-end formulation, we're optimizing each network separately. And hence why we have a separation between the encoding and the emission model and the transition function. So you can see the training the sort of the transition model here, the underscore model underscore mid, and then you've got train models underscore model underscore down in this, which tells you how we're actually doing our optimization. So again, we'll take maybe 5 minutes to look through, and if anyone has any questions at this point. I'll also keep highlighting that this is a really inelegant way. So there's lots of recent work that does it a lot better, but this is just one way of instantiating it.
I know. How does it work with the difference? So you have 3 stages: top, middle, and down. So I understand that the top one is for optimizing the policy network, but then why are there 2 stages for transitions and likelihoods?
I think it was just an architecture choice. You could have it same. So I guess from a GMO perspective, the first bit is just encoding the space and then learning the transitions. That would be one way of thinking about it. But because we don't have end-to-end learning, I think it's a little bit messy. That's why I said it's like one way of doing it, but it's quite outdated now.
Okay. And for the standard normal prior, you just use it in the beginning and then you switch over to the.
So, sorry, when you say normal prior, it's just the uninformed gamma.
Yeah, exactly.
Yep. So if you'll notice, we have a gamma. So we just like increase it over time and then we switch over. For the formulation that we're going to consider, we don't actually end up switching out from the uninformed prior because the formulation, like the environment is so simple, we don't need to. But for more complex environments, you might need to have some transition information.
Okay.
So you can have a policy conditioned elbow.
Yeah, good. Thanks.
Okay. We're going to now move on to the next bit. Again, I'm hoping people have had enough time. It's just we're also now running out of time, so we'll switch back. Okay. So we've sort of thought about how to instantiate this model, but I've sort of bypassed the issue with how do we actually collect the data to be able to learn the model parameters and what happens with the habitual network. So in our formulation that we have, we essentially equip the agent with a slow and fast planning process using uncertainty minimization, which means that when we're selecting actions, it's not the standard active inference formulation that I introduced before, but it has 3 different components that I'll just talk through. So for the first bit for the action selection, we introduced 2 intertwined systems for action. So we've got the prior that we talked about, which is the model-based action prior that we calculate using imagination, which is a result of rolling out the expected pre-energy. And it's quite analogous to the initial formulation that we discussed, where we have the summation over time of the expected free energy and a softmax over that, and then summation across all the different actions that we have. So this is a more slow and deliberative process if you're thinking in cognitive terms. So you're having to evaluate the expected free energy in the future over time. The other one is sort of a more amortized perspective, and it's the model-free neural network, which we term the habitual network. So this is this approximate distribution over the action space. And this is learning to essentially map our latent states to an approximate posterior policy. So we saw that in the code where we're inputting our state space and then we're outputting some action. And because the actions in our formulation are categorical, that's why we're essentially getting a categorical action space. So the main difference, again, in the standard active inference formulation to the one we have here is that we end up essentially supplementing the surprise of bound that we had before with an additional KL divergence. So the KL divergence that we now have is between the habitual prior, which is, the habitual network, which is this approximate that we're seeing, and the prior that we have. So this is something that I skipped when I talked about the loss bit. So we'll just go back here. So now we have this habitual loss. So we're calculating analytically the KL divergence. And so essentially calculating this by hand. And then that gives us the habitual loss that we're then using to train the habitual networks. Any questions or comments regarding this? So this is like a big, I guess, move in terms of like the formulation that I introduced before, but it means that we have a nice way of going between fast planning and slow deliberative planning, depending on how well the agent knows the environment and how well the model parameters have been learned. Okay, either it's too early in the morning or everyone's extremely happy. Okay, hello. So I'll just get to that in a moment. So essentially we have a mechanism where we introduce the weight of the approximate and the prior to learn the transition function. So it gives us a top-down attention mechanism. So that's one way of doing it. It's not the most principled, but it's one way. Any other? Okay. So I'll go. Ooh, cool. Okay. So this is what I just mentioned here. So in order to evaluate like how much weight we should during the learning process, trade-off between like the slow and the fast planning formulation, we introduce this precision term, the omega t here. And it's essentially this scale of precision that's modulating the uncertainty on the agent's estimate of the hidden state of the environment. So I keep forgetting that the laser pointer has disappeared and I'm like rolling around. Yeah. Okay, so we've got the omega term here, and that's determining how much variance we have when we're estimating our latent state or the transitions over that. So when we discussed it internally in the lab, we sort of thought about it in terms of cognitive terms first, which is that, like I said, it can be regarded as a top-down attention mechanism, which is regulating the transitions and how well they should be learned. So it could be learned in more detail or less detail, depending on how much weight you should impose on your approximate. So if the KL divergence is really high, which means you haven't really learned anything, then your omega term is going to be quite low, which means your precision is quite low. Whereas if the KL is quite low, which means that actually the prior, which is like the slow deliberative processes, and the habitual network is approximating that really well, which means then you have something that's quickly converging into a really precise belief about what the current policy should be. So this is simply, the omega term is simply a logistic function that we have. And like you can see, it's a monotonically decreasing function of the actual KL that we have. Are there any questions? Because most of the time when this is presented, a lot of people aren't comfortable with this idea because it's like a little bit ad hoc, but it provides a nice way of just having this natural form of annealing, precision annealing for when you're learning the transition dynamics. Again, maybe it's too early. That's a really good question. Tuning and grid search, it entirely depends on the environment. So for the environment that we're going to be looking at, A is 1, and then B is 25, C is 5, and D is 1.5. But for another simulation, we had something different. That's why I said it's a little bit heuristicy, the way it's been set up. And we've been thinking about like a little bit more, I guess, refined way of doing it, and that would just be like having an additional prior on top of the omega term. That would be one way of controlling how much you sort of put weight on the approximate or the prior when you're learning your policy. Okay, so I'm going to again move back to the code. So we're going to jump a little bit here, and I want you to go down to this part, which is, so if we just look at the table of contents, we're in the train model section and then looking at the training loop. And here, I just want to highlight how we're actually calculating the omega. So that's the key thing. So we online updated the omega term. And this omega term is then passed to the transition optimization objective here. So when we calculate the loss and optimize based on this loss, we're doing it online, which is quite nice. And that's why it's this nice way of annealing the precision over how well we've learned the transition dynamics. And we also do it for the lower level where we are when we start using the non-uninformed prior. So that would be the policy conditioned prior. Okay. So just quickly going back, if we look at it in the transition, so this omega term is what we are scaling our log variance with, and then it's passed through these functions as well. Okay. Any questions or comments? Okay. No, that's good. Okay, so then, yes. Sorry, would it be possible to speak a little bit louder? Would it be possible to speak a little bit? Yeah.
I have to ask the question again. Okay, I didn't saw where the omega was playing a role in the transition network code.
So the role of the omega in the transition, or
the transition network section. Yeah. If I understood well, you said that this omega is passed to the transition network.
Yes. So if I'm understanding your question correctly, you're asking where the omega terms comes in when you are actually learning. Okay. So if we play from the current slide. So you can see that the omega term is here. So it's scaling the precision that we have. And then that determines our latent state. So when we consider the sufficient statistics of the posterior distribution, the omega term constrains it because it's over the transition function. So we're like, how well have we learned the policy condition transition? So if we've learned it really well, then you would have a high variance, sorry, not high variance, a high precision. And if you haven't learned it that well yet, then the precision would be low. So that's, I guess, the background for it. And then if you go back to the code, it's coming in when we're actually calculating our KL divergence. So if we go into this bit, so it's the log variance over the posterior distribution that we have.
Thanks, it's clear. Thanks.
Any other questions? Okay, I just also realized it's like in 10 minutes the tutorial ends, so I will rush through. Okay, so planning then is so like I said, there's two systems that we have. One is like the slow process and one is the fast process. So we've just talked about the fast process and how that's helping with learning the transition dynamics by scaling how confident we are in those transitions that we have learned. The second bit is the more slow deliberative process. And for this, we're using trajectory exploration using typical MCTS. And what we end up doing is rolling out the agent's habitual network. But what I wanted to first highlight is how we're actually calculating the expected free energy. So I guess the main issue in the literature is how to actually calculate the state information gain and the parameter information gain terms. So when we calculate it, we end up rearranging these and calculate the terms using MC sampling. So for A and B, so as again, I thought I had my laser pointer and I was pointing away, but okay, so everyone can see that. So to calculate A, which is the likelihood, we're essentially doing ancestral sampling for the states and outcomes sequentially and using that to calculate the first two terms, so the likelihood of the observations and the state information gain. So for the likelihood, we're comparing the outcomes that we have essentially evaluated through the ancestral sampling process, which is just rollouts that we have with the prior log distribution over outcomes. So here, again, it's a bit of a trick, and it sort of depends on what the environment setup is, but you can constrain what the prior log distribution over outcomes should look like. So for example, in a world where like your ideal observation set for in this instance would be like all happy faces. So I would have a prior log distribution of outcomes over that. But in our scenario, it's a little bit simplistic. So you just nuance it with the context of the environment that you're setting up. For the state information gain, again, we're sampling the thetas and the states and outcomes sequentially through the ancestring sampling process. And then we're using the parameters of the neural network theta to approximate over using the MC dropout. So that gives us the state information gain formulation. And then the last one is the parameter information gain. Again, it's using the same mechanism, but we're drawing out the thetas and the states n times for this one. And for the first expectation, we're also drawing out the thetas n times. So there's a process where for this formulation, you're just sampling the S states n times, and for the first expectation, you sample it both the thetas and the S n times. Again, this can look a little bit convoluted, so we'll go to the code to make it slightly more easier to follow. So now what I want to do is have people jump to the MPC and the MCTS section using the defined gender model. So this gives you like a more explicit formulation of what I mean when I say ancestral sampling. So we're just taking an expectation with respect to the different steps when we're rolling it out. So the key function of interest here is calculating G and calculating G underscore mean. So G is when we actually use ancestral sampling, and based on like the number of samples, we roll it out X times into the future and decode and calculate the terms that we just talked about. So we don't have time to go through all of it, but what I have here is just annotations of exactly what part this is. So this is our A term. This is our B term in the, if you go back to the slides, and this is the third term C. So this is the first part of it, and this is the second. The key difference that I wanted to highlight is that you can either have a sampling-based approach, or you could have something where you're just using the mean. So that's where like the way we defined the autoencoder and sorry, the encoder network and how we sample from that becomes important, because for the standard expected free energy calculation where we're doing the sampling, then we want to use our sample-based transition and encoder. But for the one where we're doing the mean, we just do it directly without the samples. Okay. Any questions? Sorry, this is like a whiz through because it's 10:30, so it might be. Okay. Questions or? Okay. This is, I guess this is the nicest audience, but so during the so during the MCTS process, the agent is generating this weighted tree search iteratively, like you're seeing here. And then in each single MCTS loop, we're just doing a one plausible state action trajectory starting from whichever time step that we have. And then for those, we are, for the ones that we've explored before, we use the prior that we have. So this would be something that we've calculated using the expected free energy explicitly. And then the second would be the approximate if you haven't. And using that, we essentially get the weights of the search tree, which are defined by the expected free energy association with the state and action pairing. And in each round, what we're doing is propagating the expected free energy for the newly parts of the trajectory that we're exploring. And then we're back propagating that. So we're essentially at each time step, selecting these nodes, expanding them out, then simulating this MDPs of the trajectories and evaluating the expected free energy of that, and then back propagating the value of that through the tree. So yes. It's pretty slow, but it depends on the threshold that you use and how much of a depth you want. So if you have a really shallow search, then it won't take that much time. But if you've got like a really long horizon that you're considering, then it could take what? Yeah. With a non-stationary process, no. So we've got pretty deterministic setups for this particular formulation. We found that, so again, preface, because I've spent the entire tutorial talking about how nice this and easy this framework is, but the architecture is really simple. So if you get into like more complex environments, the feed-forward architecture wouldn't be able to handle the transition dynamics. So so you can use the prior information from the habitual network. So that easier. So you are alternating between the thing that where you're explicitly calculating the expected free energy, one where you're using the amortized habitual network. So that does alleviate some of the computational pressure. But again, it depends on the breadth of the tree and like how many nodes you're expanding out every time when you do like a step-by-step process. So I think it's a open-ended question as to what is the best way to do this. We haven't worked on the MCTS in the same way because we found that it wasn't computationally the best. It just takes a long time, but it's quite nice in terms of performance once you sort of say, okay, I'm just going to deal with how slow it is. Sorry, that's a caveat. Okay. So I think I'm conscious that we are running out. We have run out of time, so I will. Yeah, okay, so we'll quickly wrap up. So I think I've spent maybe too long making sure everyone is set up, but essentially I can highlight some key bits in the code and then we'll just quickly conclude. So this is the active inference MCTS code. Again, you can make it a little bit more cleaner, but you can see we're alternating between using the habit depending on the thresholds you're setting, and we use an upper confidence bound threshold to calculate that. And then you're repeating your cycle for however broad your search would be. And that's where like the intensity in terms of the computations comes in. So we use that formulation to calculate the expected free energy trajectories. And in the code, when you look at it, this particular function, sorry, going up here, the demo active inference model, it's got the calculate the expected free energy or the G given trajectories, and that's what we're using during the MCTS formulation. And this one doesn't have the ancestral sampling, so we are sort of alleviating the fact that we haven't had to calculate like 10 or something samples. We're just using the distribution directly. Okay, and then the last bit that I wanted to highlight is that you can run this model yourself. So these are the parameters that we used in the results I'll just briefly show. So we're defining it over a simple environment that you downloaded at the start. And as you'll notice, we're optimizing everything separately. So we optimize the top model, the middle, the transition model, and the down or the variational architecture separately. And then this is just logging some statistics and making sure like things are working as well as we would expect. So this one hasn't converged, but I just wanted to show like what the sort of reconstructions would look like. So if you were considering the current time step for the just sprites data set that we downloaded, and then you consider the next time step, you can see when you're just doing the reconstruction is pretty decent. Again, it's a really low fidelity model, so with more complex environments, it doesn't perform as well. But again, you would have to nuance the architecture based on the requirements. And if you do manage to find time to train it, you can plot the actual tuning curves to see how well different parts of the model are optimizing. So you can see, at least when I stopped, it hadn't converged in terms of the policy, but you can sort of take longer to see what's happening. So I let you sort of look through that in your own time, and then some traversals post-learning. So this is going back to the question that we had in terms of what are the parameters really denoting. So in an optimal scenario, what you would have is a true understanding of what the latent states in the environment are. And then based on what you've learned, you could do some sort of correlation mapping. So we can see that over here that with our 4 true latent states plus this reward function, each of these are sort of in each of the latent states. So we have 10 are encoding something slightly different, with the last one encoding the reward, as you can see through this bar over here. Okay, and then I think we'll just skip this part. I'll just take your word for like, well, yeah, you have to take my word for the fact that everything works well. Again, preface with the fact that the task is quite simple, but then we test it out with something a little bit more nuanced, with the same architecture that we just walked through. And we can see that with model free RL is working really well. But we've done some further work with the same architecture with a little bit more complexity in the visual input, and it doesn't perform as well because the encoding and the actual reconstructions aren't appropriate because it can't really map back the original images that well, which then means that the policy can't be learned. So whenever you're dealing with these type of formulations, it's good to like think about how each part is working, and it's only once you've learned the encoding appropriately can you actually learn the policy on top. Yeah, so I just wanted to close up with like open challenges, I guess, for the field of active inference in terms of scaling up, which I'm sure like everyone is. I just realized that it wasn't full screen, sorry. But there's lots of bits in terms of encoding the right joint model. So I sort of alluded to the fact that what the architecture we presented is quite simple, but there's problems in relation to hierarchical models in terms of trying to have the right sorts of structured representations, and also being able to decompose those structured representations in a meaningful manner when you're actually making use of your joint model. And then the other side is planning in terms of hierarchical planning, meta control, and preference models, which I'm really interested in. So I've highlighted some temporal bits which I'm working on and have some work out on. So if anyone's interested. So I'm just going to close off, and so sorry for taking so much time, and also thank you everyone for listening. But I wanted to say thank you to my collaborators, so Zaf, Pedro and Carl on the project that I presented, but also to other collaborators who I sort of had snippets of at the start of the presentation.